Okay, let's start today's lecture with discussing formal charges. So the formal charge, the technical definition is the formal charge is equal to the number of valence electrons minus half of the bonded electrons minus any of the non-bonded electrons on the atom. So, for example, let me show you a particular structure, and we'll see if we can calculate the formal charge of a particular one. So we're going to do SCN minus. So as we classically would have done, we're counting valence electrons first. So sulfur has 6, carbon has 4, and nitrogen has 5. And then we've got this extra one, so we add in one more. And when I add all those up, I get 16 total electrons. So as we would have done before, we would have predicted, okay, well, which one's going to be the central atom? And we usually predict the one that has the fewest number of valence electrons would be our central atom. So I'd predict carbon in the middle. So I put my carbon in the middle, I bond my sulfur, I bond my nitrogen, and then I obey the octet rule by adding electrons in pairs. Each sulfur gets 6, each carbon gets 4 more, and the nitrogen gets 6 more as well. And when you count this up, we don't have 16 electrons, we have 20. So we don't have the right number of electrons, so the strategy was, well, remove pairs of electrons from each of the side atoms and replace with a bond in between. So when we do that, we could reduce the number of electrons by 2. So now this structure doesn't have 20 anymore. Now, because these electrons aren't here on each of the elements, instead they're shared in between, we now see that we have only 18 electrons in there. And then we have choices of what we could do from there, right? We could have a double bond to the sulfur, right? And keep that double bond to the nitrogen, with its 2 pairs of electrons. Whoops, that's supposed to be a pair. And then this sulfur's would have 2 pairs of electrons on it. Or we could triple bond to the carbon. Triple bond the nitrogen to the carbon and leave the sulfur with its 6 electrons. So we're going to look at identifying which one of those is the best option. And the way that we do that is formal charge. So, for example, and I'll do this in red, the carbon in the middle, in both cases, starts with 4 valence electrons. So it's got 4 valence electrons. We're going to subtract half of the bonding electrons. So there's 8 bonding electrons in the middle. So half of that is 4. There are no non-bonding electrons on the carbon, so therefore 4 minus 4 is 0. In other words, its formal charge is 0. And what that means is, since carbon has 4 valence electrons, since it is contributing all 4 of those electrons to the bonds that it's making, we say that it has no charge. It came in with 4, it's using 4, therefore it's doing what it's supposed to be doing. It's got a formal charge of 0. Same thing for the carbon down here. Each electron in those bonds is a bonding electron, and so it started with 4 and it's contributing 4, it's still 0. But the sulfur and the nitrogen are not the same for both, and so we're going to see if we can determine which one it is, which each one is. So let's do the sulfur in this particular case. So the first one. The first sulfur, it comes in normally with 6 valence electrons. It has half of these 4 electrons that it owns. So in other words, it's contributing 2 electrons to those bonds. So that's, actually let me do this in green just to make it more clear. It's contributing, whoa, hello. Yeah, that did not work. It's contributing this electron here and this electron here to that bond. And then it also owns 2 more pairs of electrons. In other words, 4 more electrons. So 6 minus 2 minus 4 is also 0. Came in with 6, it's using all 6, so its formal charge is 0. I'll do the nitrogen in blue here. So the nitrogen on the right-hand side comes in normally with 5 valence electrons. Let's subtract the bonding electrons. There's 4 bonding electrons that nitrogen is surrounded by, so it's contributing 2 from those, so we're going to subtract 2. And then we're going to subtract any pairs of electrons. It's got 2 pairs of electrons on it as well, so we're going to subtract from that 4. And you'll notice nitrogen has a -1 charge overall. So the formal charge of carbon is 0, the formal charge of sulfur is 0, and the formal charge of nitrogen, let me move this real quick, formal charge of nitrogen is -1. Okay, let's do the same thing in the one below. So again, carbon had a formal charge of 0. It starts with 4. It's contributing 4. Let's do the sulfur again. We'll do this in green. So the sulfur comes in with 6. Let's subtract from it the bonding half of the bonding electrons. So there's 2 electrons here in the bond, so it's contributing 1 of those electrons, so -1. And then it owns 3 pairs of electrons down here. So that's 6 non-bonded electrons for a grand total of -1. So the sulfur formal charge on the bottom structure here is -1. Let's do the nitrogen again in blue. Nitrogen comes in with 5 valence electrons. It owns, or I'm sorry, it's contributing in the bond. I did it again. It's contributing in the bond 6 of these bonding electrons. It contributes half of those, so it's contributing 3. And then it still owns a pair of electrons that are not bonding, so it's got 2 of those. In other words, 5 minus 3 minus 2 is 0. So you might say to yourself, well, these atoms, 2 of them in each of the molecules have a formal charge of 0, and 1 has a formal charge of -1. So which one of these 2 structures is more likely to happen? Well, we can predict the stability of the structure by 2 possible scenarios. Number 1, the lowest formal charge, or the way we're going to kind of say that is the closest to 0, is going to be the most stable. Hopefully you can see my air quotes that I'm putting around stable, is the most stable structure. Okay? So the closer we can get to 0, the better it is. In other words, if I came in with 4 electrons, I'm using 4 electrons. That is maximizing the use of those. If I came in with 4 electrons and I'm suddenly have no electrons on me, which is not possible, I've got a +4, that's not good in terms of covalent bonding. The second possibility is that, or the second prediction here, not only do we look for formal charges closest to 0, because those are the most stable, but we're also going to look to make sure that the most electronegative element has negative charges. So the more electronegative an element is, the more likely it is to attract an electron. So it's more likely to have the negative charge than another element. So if we're looking at these 2 scenarios, between sulfur and nitrogen on the periodic table, here's nitrogen, here's here's carbon, here's oxygen, here's sulfur. Sulfur is a whole row down. So we would predict that nitrogen, even though it's one column to the left of oxygen, oxygen's family, we'll still predict that nitrogen has a higher electronegativity because it's down a level, so the electrons are closer to the nucleus. So we would predict that it would have a higher electronegativity. And we could look those values up if we really wanted to. Nitrogen is near electronegativity of about 3, and sulfur is about 2.5. So they're not far away from each other, but nitrogen is still the more electronegative element. So which one of these 2 structures has the negative on the more electronegative element? That's this structure right here. So this is actually the most likely structure to occur, where we have double bonds on both sides. Okay, let's continue. So we can predict, I've got another one for you here, which molecule has, which resonance structure has a better stability. So these were 2 examples of sulfur and carbon and nitrogen. Let's do one that contains nitrogen and oxygen. So this is N2O dinitrogen monoxide. Again, the nitrogen comes in with 5, and there's 2 of them, plus the oxygen for a grand total of 16. We normally would bond the nitrogen. to the other nitrogen, right? Another possibility is that the nitrogen is bonded to the oxygen in the middle. So the question is, which one of those two exist? Let's do the one on the left first. So we could obey the octet rule for the nitrogen and for the oxygen, right? Adding 6 electrons to each. When you do that, you've got 20 electrons. We're back to the same scenario that we had before. So the two possibilities are that as we start removing electrons, we end up with 2 double bonds, and each oxygen and nitrogen on the side has 4 electrons, or we'll end up with a triple bond, and there's a couple possibilities, right? We can triple bond to the nitrogen, or we can triple bond to the oxygen. So all 3 of these are possible structures that would result from this. The other one, in this case, an N on each side and the O in the middle, because this also, wow, my pen is crazy today. Well, this has also 20 electrons. We need to get to 16, but now the oxygen in the middle, we would guess would, I guess we're back to the same issue. We can triple bond, we can single bond. Most likely people would draw this structure as O with 2 double bonds. Let's see if that indeed is good. We could also have a triple bond to either side, but you're going to see that this is a terrible structure, and I'll show you why in a moment. I'm going to do formal charges in red, and I'm going to write them below or above each element. Let's look at this structure, and I'll tell you why this one is bad. So the O in the middle starts with 6 valence electrons. It's contributing, of the 8 bonding electrons, it's contributing 4 of them, and it has no non-bonded pairs of electrons. So 6 minus 4, it has a formal charge of +2. I'm going to write it in parentheses because it's not a real charge, it's just kind of a fake charge, but we'll write it there. And then the nitrogens on the side, each one starts with 5 electrons. Of the 4 bonding electrons, it's contributing 2, so 5 minus 2, that's 3. And then still has 4 of these non-bonding pairs of electrons. Or in other words, it starts with 5, we subtract 2, we subtract 4, it's a -1 charge, formal charge. And the same thing for the other side. It's the exact same. So we've got a +2 in the middle, 2 -1s on the outside. Those are not close to 0. I mean, their -1 is close to 0, but a +2 is quite a bit further away from 0. This is not a great structure, so hopefully one of the other structures on the left here is a better formal charge, because this, the one on the right, is not very good. So let's look at the double bonded N, this top one here. Nitrogen starts with 5. It's got, of the 8 electrons that are bonding, it owns 4 of them, so that's 5 minus 4, or in other words, it's a +1 charge. The nitrogen on the left starts with 5. It's contributing 2 of the 4 bonding electrons. It owns 2 more, just like the other one that we just did. It's a -1. And then the oxygen on the right side starts with 6. It's contributing 2 of the 4 bonding electrons here, and then has 4 more on the side, right, 2 pairs. So its formal charge is 0. So if you were choosing between this structure or this structure, which one of those two would be a better formal charge? Well, the one that has closer numbers to 0 is the one on the left. So for that reason, we would not draw NON as our structure of N2O, because that is not as good a formal charge as our first. Then, if we were comparing that to, let's say, one of these down here, the nitrogen in the middle, again, has only 4 electrons, and it started with 5, so its formal charge is +1, excuse me. The nitrogen here contributes 3 of these 6 bonding electrons, and it owns 2 more. So if it starts with 5, contributes 3, and owns 2, that's 5 minus 3 minus 2. This nitrogen is a 0. Starts with 5, and it's got 5 electrons essentially on it. And then the oxygen here starts with 6. It's contributing 1 to this bond, so 6 minus 1, that's 5. And then it owns 6 more electrons, so 2, 4, 6 electrons, so it's a -1 in charge. So if we were looking at these two formal charges, they are identical. Both have a +1, both have a 0, and both have a -1. However, between these two, oxygen is the most electronegative element between nitrogen and oxygen. So this structure would be preferred over the top one because it has the negative on the more electronegative element. And surprise, surprise, if you look at the bottom, and I'm just going to show you the oxygen's one right away, you're going to see something very bad happen. Again, oxygen comes in with 6 electrons. Of the 6 bonding electrons, it contributes 3, so 6 minus 3 is 3, and it contains 2 more, so 3 minus 2 is 1. The oxygen is a plus 1. That's going to not be good, especially since the nitrogen in the middle, remember, had 5, it's contributing 4, it's a plus 1. This one is especially bad because you have 2 elements next to each other that are both positive in charge, in formal charge, which is like it's got a charge inside the atom. And so 2 positive charges next to each other are not very good. But the other part that's in the issue is nitrogen, with its 5 valence electrons, would contribute 1 of these 2 bonding electrons, so 5 minus 1, that's 4. And then it owns 6 more, so 4 minus 6 is a negative 2. So we see here that this nitrogen is not only has the electrons, but has more of the electrons than the most electronegative element in the atom, which is oxygen. So we don't see this as a high likelihood of being the molecule structure. So this satisfies formal charge the best. A triple bond to the nitrogen on the left and a single bond to the oxygen. Okay, that was a lot of talking. Let me try to finish up these last few here. So looking at bond properties, again, strength has to do whether or not we have a single or a double or a triple bond. Certainly, the more bonds present, the closer the atoms have to be in order to share those electrons. And the closer you are, the stronger that attractive force to electrons. Bond order is essentially how many bonds are being formed between the atoms. So in the case of, for example, the nitrogen to the oxygen here, we have 2 bonding electrons, and there's 2 atoms, so that's a single bond. The definition of, well, let me erase that. That was silly. Let me do this. Let me do the definition first, and then we'll define it. So technically, the bond order is defined as the number of bonding electrons divided by 2. So the oxygen nitrogen here has 2 bonding electrons over 2 atoms. The bond order is 1. It's a single bond. The nitrogen here has 3 bonding electrons. 3 pairs of bonding electrons, so 6 bonding electrons divided by 2. That's a triple bond, right? A bond order of 3. And then also, environment plays a role in the bond properties. So the higher the electronegativity of the element, the more that element will draw the electrons towards it. So if we're looking at that N, triple bond N with a single bond O, so the more electronegative element is the oxygen. So we're going to see the oxygen drawing electrons closer to it. This is the international symbol for drawing electrons towards it, which in turn draws the electrons. Since nitrogen's kind of getting its electrons pulled on it by the oxygen, it's in turn going to start pulling more on the bond or the electrons in this triple bond as well. So we end up seeing a little bit of disparity between the bond strengths of these two. This NO single bond, since the electrons are being kind of pulled away and pulled from the nitrogen-nitrogen bond, this actually weakens this triple bond because the oxygen's pulling on those electrons. It also causes the molecule to be polar. So because the electrons are being pulled towards there and because the formal charge is -1, we say that this oxygen is partially negative. That's the little Greek symbol for lowercase delta. It's partially negative because it's drawing the electrons away from the N, and that causes this N in the middle and consequently the N kind of on the side to be partially positive. This end of the molecule becomes positive. And so we have a disparity of plus minus in the molecule, and because there is a disparity, there's one side that is more negative and one side that's more positive, we end up with a polar bond. This also makes a polar molecule, but we'll talk about that in a little bit. Let's see. Bond length, again, is always defined as the distance between the 2 nuclei. So in order to get an NO single bond, these two don't have to be that close in order for their electrons to overlap, but to do an N triple bond, in order to overlap those 6 electrons, these have to be much closer. So this is a triple bond is a very short bond. The atoms have to be very close in order to overlap those electrons and share them, whereas a single bond is much longer. And then it depends also on the size of the atom. So if I have a hydrogen bonded to an oxygen, that's a short bond because hydrogen itself is a very small atom. If I had instead barium, this is a terrible example, but I'm going to use it, barium bonded to an oxygen, barium is a huge atom compared to the hydrogen. So this barium-oxygen bond would be very long. The other part is that bonds vibrate. So the frequency of vibration is typically between 10 to the 12th and 10 to the 14th hertz. And so the higher the frequency, so if we can measure the bond frequency, if the frequency is higher, that tends to mean that the bond is stronger. So we would see a triple bond, for example, to have a very high frequency for its bond, and so therefore a much stronger bond. All right, let's stop here and then we'll continue with bond energies in a moment. Okay, so to continue on, if we're looking at bond energies, the definition of bond energy again is that when you break bonds, that's endothermic. It costs you energy to break a bond apart, and when you're forming bonds, it's exothermic. It releases energy when you form a bond. Let me show you a quick simulation of that. That is not the simulation. So here we've got 2 atoms. Let me stretch this out a little bit for you. So here we've got 2 atoms that are near each other. They've got electrons, and we're going to move the nucleus closer to each other. Move this away. And then we're going to graph the potential energy of that. So the graph is going to display here. So as I start moving this, as I start moving this electron, or this nucleus, notice that we're starting to get a lowering of the potential energy as it gets closer and closer to that other nucleus. And hey, look right in the middle, look what's happening. And it's hard for me to even keep it there. It's starting to draw itself in. But the electrons are being shared now between those 2 atoms. And there is a natural tendency, since both protons are attracting the electrons, to kind of keep them there at that distance. If I keep squeezing them together, notice what happens to the potential energy. It spikes way up. Again, we have some proton-proton repulsion there when I get that really close. So we see it spike way up. And then the natural bond distance is that lower part in the bond energy, or in the potential energy, right? That natural bond distance, the lowest part of the energy. So the bond is actually formed as I bring them closer, and it releases energy. So a high bond energy means you have a very strong bond, and a low bond energy would mean you have a weaker bond, but also a low bond energy tends to indicate that you have a longer bond because it must not be as close to the other atom. So single bonds tend to be between about 140 to maybe all the way upwards of about 570 kilojoules for every mole to break that bond, or would be released when you form that bond. Double bonds tend to be anywhere between 400 and 720 kilojoules per mole. Again, takes more energy to break them. More energy is released when they're formed because it's a stronger bond. And then triple bonds, depending on what it's between, anywhere from about 800 to about 1100 kilojoules per mole. Again, much stronger bond, so it requires much more energy to break. We did the bond energies in the previous unit, and we can do those for reactions as well, but now we're maybe a little bit more adept at drawing Lewis dot structures. I'm going to do letter B for you since that one is a little bit more difficult. You can do letter A. If you solve letter A, you're going to get negative 183 kilojoules. So see if you can do that. Don't forget to balance your reaction first. Let's see, letter B, when I combust formic acid, the best thing to do to solve these is to draw Lewis dot structures. So not only can we write the formulas, right, as we combust formic acid plus oxygen making CO2 and H2O. The balancing is not too hard, just need a 2 and a 2 and a 2, but we can draw Lewis dot structures and therefore identify the kinds of bonds that we're breaking. Here the carbon goes in the middle, we bond the hydrogen to it, oxygen ends up double bonding to one of them and single bonding to the other, and then the hydrogen, again, is written as it's drawn. So if you have struggles with drawing that kind of a structure, do some more practice. Maybe try the online homework. The oxygen, if we do the Lewis dot structure, is double bonded. And then carbon dioxide is double bonded on both sides. Again, I'm skipping the actual drawing of Lewis dot structures. You should be a little bit more adept at doing this, so hopefully you can see some of these. If you're not, you should have paused the video and tried it. Okay, so these are all the bonds that we're going to break. We're going to break all of these, and we're going to form all the bonds of our products. So in terms of the broken, we're going to look up values of all the different bonds. Here we've got, for our broken, we have a CH bond. How many of them are we breaking? Well, it looks like we have this bond here. So there's one bond to break, but it happens twice. So it happens 2 times. And then the value we can look up in our bond energy table. In this case, it's 414 kilojoules per mole. We are going to break a double bonded oxygen. That's this bond here. And it, again, there's one of them, and it happens twice. And that value is 715 if you look it up in your chart. We have a carbon-oxygen single bond. There's one of them, and it happens twice, and each carbon-oxygen bond is 351. We have an OH bond. There's one of them in the molecule, and it happens twice, and each OH bond is 464 kilojoules per mole. And then we have an OO double bond, right? That's the last one here. This needs to be broken as well. There's one of them, and there's only one, according to the balanced reaction, of them that needs to be broken, and that's at 498. So if you do the math on those, you get an overall value of 4,386 kilojoules in order to break all of the bonds of all of the molecules of the reactants. Let's turn our attention to the formed bonds on the right side. So in terms of forming bonds, this one we don't have as many types of bonds to form. We have some CO double bonds, which again, there's 2 of them in the molecule, right? There's one here and one there. And it happens twice. So it's 2 times 2 of them. And each CO double bond is 715 as we saw before. But since we're forming, we're going to put a negative sign on that. We also have an OH bond. There's 2 of them in the molecule. Again, this one here and this one there. And by the balancing, we have 2 molecules to form. Each one we saw before was 464, and it's negative because we're forming those bonds. So when we add up the energy that's released when we form the bonds of our products, I got a value of negative 4,716 kilojoules. So we're going to release 4,716 kilojoules when we form those bonds. So the total delta H for the whole process is going to be add in 4,386 kilojoules as you break those bonds, and then you're going to release 4,716 kilojoules when you form the bonds of your products. Or in other words, for an overall change of negative 330 kilojoules. Overall, when things bond, we're looking for an overall release of energy. the lower in energy that you are, the more likely it is to happen. You saw that with my simulation here. The bond occurs when I maximize the attractive force between the protons and the electrons, and I minimize the repulsive force between the protons and the protons. So bond formation overall releases energy. And that causes these atoms to stay where they're at, the formation of a bond. So overall, when I'm creating a reaction, it happens because we're lowering the energy overall of the system, and that keeps them where they're at. Just to finish this off, we can also make ionic crystals. So in an ionic crystal, we have alternating positive and negative charges, positive here and negative here. And we can estimate the amount of energy that's needed to create that lattice of positive and negative. So in other words, we take our negative and we add it to our positive, and we form that ionic compound. Typically, since this ionic compounds are typically solids, ions don't exist except for in solution, or if we give a lot of energy to the atoms, we can get them in gas phase. So this technically can only be done mathematically by assuming that these two ions are gaseous and that when they react together they form a solid. We can do it in solution, but it's a little bit trickier. So what are we essentially going to do? Let's say we're trying to make sodium and chlorine, which is Cl2, form sodium chloride. In order to do that, notice we balance with some 2's. In order to do that, sodium starts off as a solid, chlorine starts off as a gas. So the first step in the process has to be to take the sodium, which is a solid, and give it enough energy, so add in some energy, so that we can essentially turn it into sodium plus as a gas. That takes a lot of energy to do. That's the sublimation of sodium, right? Take sodium and turn it into sodium gas. That's the fusion and the vaporization added together is the sublimation. That requires 108 kilojoules for every mole of sodium. And then I got to take that sodium, I'm skipping down here to C, I got to take that sodium and I got to pull off an electron and make it into sodium ions, Na pluses. Well, that's ionization energy. That takes some energy as well. That's 496. So essentially, to take this from sodium solid up to sodium gas, I got to take 108 kilojoules to turn it into the gas, and I got to take 496 kilojoules to rip off that proton, or rip off that electron, excuse me. I've also got to take chlorine and turn it into Cl minus as a gas. So to do that, well, it looks like I've got to start at a Cl2 and I got to end up with a Cl. So I've got to break that bond. I've got to break the chlorine-chlorine bond and turn it into just a single Cl. That's the dissociation here reaction of chlorine. Take half of a chlorine molecule, essentially. That's a bond energy. I've got to break that bond in between the two chlorines. And then lastly, I've got to ionize the chlorine. Well, when we add an electron to chlorine, that's the electron affinity. And we know that chlorine is attracted to electrons, so that's actually going to lower its energy a little bit as it forms. So we're going to add in our 120 to break the bond, but then we're going to get some of that back as we form the negative ion of chlorine. So we're going to get negative 349 kilojoules as it forms that ion. And so by the time we're done, we should be able to add these all up, add all these values up, and get our overall lattice energy from that, right? So we can use that to estimate the delta H of this process. So if I take, so let me stop there. So here's the sodium in energy, here's the chlorine in energy. When they reform, when they form the bond between them, so they form this ionic solid, we're going to release energy, right? The whole thing overall is going to drop down. It's going to drop down by the lattice energy. In other words, the energy that's associated with the positive attracting the negative. It's going to release 786 kilojoules per mole of energy. So we're going to give off 786. So we're going up to ionize, going up to ionize, well, to break and ionize, and then we're going to release when we come back down. This is called the Born-Haber cycle. So if I take the sodium and I add a half of a chlorine to it, and I had balanced it with 2's up there and I mistakenly did that, and I form my sodium chloride, the overall delta H of that process is going to be the addition of all of these steps together. Okay, that's enough for now.